Okay, class, what we're going to do next is basically a very short survey of the different functional groups in infrared spectroscopy. So we'll start with the alkanes and the alkenes. So if you remember correctly, what we did when we're talking about how samples were prepared for infrared spectroscopy, one of the sample types was called a neutral mole, which was a mineral oil that you would suspend your solid in. So if you're ever going to use a compound to do that, what do you want is it to have a very simple infrared spectrum. And that's exactly what this slide is basically showing. So let me see if I can get my straight chained alkane. Very simple infrared spectrum. The key points for all alkanes, remember, is what we want to be looking for is the CH stretches in the region just below 3,000 wave numbers. And that's remember, that line's the demarcation line between an sp3 and an sp2 hybridized carbon stretching with a hydrogen. So in both of these cases, the spectrum is very simple. You'll see CH2 bends, a CH3 bend, long chain, sort of weak long chain absorption in the fingerprint region. But with simple alkanes, they're very simple, they have very simple infrared spectrums. The next one we look at is a cycloalkane and a cycloalkene, just to show you the difference between the two when it comes to how the spectrum looks. So with cyclohexane, we've got our CH stretches, again, below the 3,000 wave numbers. CH2 band, remember every carbon here is a CH2, and the disappearance of the long chain band in the fingerprint region. But once we introduce the double bond, the spectrum changes quite a bit. And there's a couple of key points to remember with this. The first is the CH stretches. So now we see a sharp peak right above 3,000 wave numbers, which corresponds to the CH stretches here. So there's that line at around 3,000 wave numbers between the two. So that's the first thing to notice. Second thing we'll notice is that the carbon-carbon double bond stretch is actually here, and it's quite a weak absorption, transmittance of around 65% or so. So it isn't the strongest absorption on the spectrum by far. And remember, if one of the things to make a bond really IR active is to have a change in dipole moment over time. And carbon-carbon double bonds don't necessarily have that. And the more symmetrical they are, the weaker the absorption will be. So keep that in mind. But the really powerful elucidation part for this is the out-of-plane bends, carbon-hydrogen out-of-plane bends. And so, and here we're going to be using the fingerprint region for that. And for the cis double bond, there is this out-of-plane bend, which we'll get to a bit later on. But that is one of the important diagnostic sort of things to look at. So CH stretches above 3,000. You can look for the carbon-carbon double bond, but also the out-of-plane bends in the fingerprint region. And we'll show a couple other examples. So monosubstituted double bond in this case. So again, we get the same sort of thing. There's 3,000 wave numbers or somewhere around here. CH stretch above it for the protons on the double bond. All of the saturated carbons CH stretches are below 3,000. You'll notice that the peak this time, the carbon-carbon stretch is stronger, and that's because it's a monosubstituted double bond. They tend to be stronger absorptions because the molecule is less symmetric. Then we see the outer plane bends, two really big peak strong absorptions here, centered around 1,000 wave numbers and 900. We're going to see that these correspond to a monosubstituted alkene. All right, there's another little thing to note here is that there's an overtone peak, which could be easy to miss because it isn't a particularly strong one. What we're going to see when we talk about aromatics is that this is something which is really important when we're looking at aromatics. That's on the next little slide, the next little presentation. So here are two more examples, and really this is just showing the difference between a cis double bond and a trans double bond. So in each case, the CH stretches are right around 3,000, right above 3,000. The cis double bond, you can see this absorption is far stronger than the trans, so it's almost entirely missing, and that's a common characteristic with trans alkenes. But the final point that to distinguish between the two is the out of plane bend. So in the cis, we've got this very strong peak at around 700 wave numbers, whereas the trans, it's somewhere around just under 1,000, probably 950. So there's a big difference in the fingerprint region with the out of plane bends. So there's a couple of, right, last thing I thought I'd show you is a triple bond. There are two types of triple bonds. What we would call an internal or a terminal. If the double bond's at the end of a chain or if it's in the middle of a chain. So remember, molecules that are symmetric, carbon-carbon double bonds, carbon-carbon triple bonds, tend to, when they're symmetric, the absorption can be absent entirely. So this is what this is showing. There's absolutely no CH stretch in the region where it should be. Of course, there will be no carbon-hydrogen stretch for the triple bond because it's internal, so that's missing. But if you had a terminal alkyne, you should see something at around 3,300 wave numbers, and it's quite a strong peak. And if you had a terminal one where the symmetry of the molecule is missing, then you would expect to see another peak around here. And both of these peaks show up in areas where there isn't a lot of other things, so they can be quite diagnostic for that. We'll do an example of a triple bond in our assignments, so you can see those firsthand. So here's basically a little chart to like sort of a cheat sheet, so to speak. So remember the boundary around 3,000 wave numbers. Anything higher than that, we've got sp2 hybridized carbons. Anything below that is sp3 saturated carbons. The exception is aldehydes. We'll talk about those when we look at carbonyl compounds. Triple bonds are up at 3,300. There is the odd saturated system, which has got some ring strain like a cyclopropane, which will be above 3,000, but by and large, once you get above that 3,000, you've got a carbon-carbon double bond, like the stretch for that. We're not going to talk too much about the sp3 hybridized stretches in this for methyls and methylenes and methynes. That's really less important for what we're looking at. So when it comes to the carbon-carbon double bonds, so Remember, these are weaker than carbonyls because they are not as polarized. And it really depends upon the substitution. So if you've got a monosubstituted, you'll notice that the wave numbers of these vary between a mono or a di or a trans or a cis or a tri or tetra. So these are often missing because of symmetry. So these wave numbers do change a bit, but it makes less sense to use these numbers to figure out if it's mono, di, or trans, because there's other things which can influence the location of double bonds, in particular conjugation. The better place to determine the substitution pattern is with regard to the out-of-plane bands. So we'll look at that next. So remember, carbons are sp, alkenes are sp2, sorry, trigonal planar sp2 hybridized. So this little proton is wagging up or it's going down. So it's going out of the plane. And here, what we'll see, this is where in the fingerprint region where it becomes quite clear what the substitution pattern we have. So mono-substituted, you'll have two peaks, one at 1,000, one at around 900 wave numbers. For cis, there's a range between 650 and 750, and it's a strong absorption. For trans, the range is far less. It's around 950 to 960 or so, and it's strong. When you've got the two substituents on the same carbon, it's around 900, just below 900. And then when you get into the tri, you've only got one hydrogen here. So this tends to be weaker, so it's only a medium absorption, but it's centered around 800. And of course, if it's a tetrasubstituted alkene, there's no hydrogens, so there is no out-of-plane bands, right? All right, so that's basically the section on alkanes and alkenes, and we threw in a little alkyne there just for fun.